All right, let's try and cut through some of the noise today. How do we quickly get a real handle on powerful programming concepts, like object-oriented programming, especially when we're looking at a language like Ada?
Yeah, Ada isn't always the first language people think of for OOP, but it has a really robust approach.
Exactly. It's maybe not in the everyday tech headlines, but it has its own unique way of doing things, and that's really what we want to unpack today.
It's definitely more than just learning new syntax. It's about understanding the core philosophies behind how Ada was designed, even if it feels a bit different at first.
Right. And sometimes those different approaches offer some pretty elegant solutions. Very precise.
Very explicit, yeah.
So that's our mission for this deep dive. We're looking into the object-oriented features of Ada, and we're using the Ada Quality and Style Guide as our map, really. It's the resource for understanding Ada's way.
It really is.
We want to pull out the most important ideas, the nuggets about how Ada handles OOP, its syntax, its design patterns, so you feel, properly informed. Maybe even a bit surprised by how it tackles things.
Okay, so maybe we should start with the basics. Just lay out the core OOP ideas we'll see in Ada, based on its own rationale from 95.
Good idea. Where do we start?
First up, encapsulation. Pretty standard idea, bundling data with the operations that work on it, keeping the internal details hidden away.
Got it. Data and its methods together, keep the insides private. What's next?
Then there's inheritance. Ada thinks of this as incrementally building new abstractions from existing ones. And the key is, without messing up the original, it's really about extending functionality.
Okay, so building on what's already there safely, like adding features.
Exactly. And third, polymorphism. This is about programs working with common properties across different kinds of objects, sort of factoring out their specific differences.
And Ada handles this in a couple of ways, right?
Yeah, two main ways. There's static polymorphism, which you often get with generics. The compiler figures things out early on.
Telltime decisions.
Right. And there's dynamic polymorphism. This uses what Ada calls class-wide types. The program decides which operation to call at runtime, based on a hidden sort of tag on the object that identifies its actual type.
Okay, runtime decisions based on the object's true identity. Makes sense. And we probably need Ada's specific definitions for a few terms, too.
Good point. So in Ada, a type defines a set of values and the operations you can do on them. Simple enough.
Right.
A class is a set of types, all related by derivation. So if you derive type B from type A, they both belong to the same class. They share common stuff.
A family of related types.
Exactly. And an object is just an instance, a variable or constant of a specific type or class. It holds a value.
Perfect. Okay, definitions down. Let's get into section 1, the foundation. Tagged type hierarchies in Ada. Where does good Ada OOP begin?
Well, like most things, it starts with good design. You need meaningful abstractions, clear class hierarchies. That's universal.
Sure.
But Ada specifically emphasizes, through the style guide, using child packages to organize things. Think of them for structuring subsystems, creating reusable frameworks. It's Ada's way of ensuring clean modularity. Guidelines 4.1.1, 4.2.2 cover this.
Okay, so child packages provide the structure.
Yeah.
How does Ada actually do inheritance then? What's the mechanism?
That's where tag types come in. They are absolutely central. Inheritance in Ada is primarily about implementing an is-a relationship. Generalization, specialization.
So like saying a checking account is an account.
Precisely. It's done through type extension. And this is a key point. It's generally not used just for bundling modules together like you might see elsewhere. It's really about that is link.
Okay, focus on the relationship.
Yeah, the style guide says it directly. Consider using type extension when designing an is a hierarchy, and also use tag types to preserve a common interface across differing implementations.
So if you have different kinds of shapes, but they all share some shapeness, tag types help manage that common interface.
Exactly. Let's take that geometric objects example from the guide. You might have a base object type, maybe just with X and Y coordinates.
Okay.
Then, to make a circle, the Ada syntax is super explicit. Type circle is new object with record radius, float, and record. See that with a record part.
Yeah, it's pretty clear it's adding something.
It literally means this new circle type adds a radius component to whatever it got from object. You could even have a point type. Like type point is new object with null record. It adds no data, but it still is an object and part of that hierarchy.
Okay, so the with record is key for extension. Now, you mentioned tagged type specifically. What if a type isn't tagged?
Ah, that's a crucial difference. If you derive from an untagged type in Ada, you get a completely new, distinct type. It has the same implementation, sure, but you cannot extend it further with new components. It enforces very strong type checking. but it's rigid in that way.
Right. No adding fields later.
But when you derive from a tagged type, that's where the OOP flexibility comes in. You can extend it with new components. And this is what forms a class in Ada's terminology.
And that allows?
That allows for class-wide operations, overriding primitive operations, basically. It enables Ada's dynamic polymorphism. It's fundamental.
Okay, tag types are the key enabler. Now, how do we handle collections of different objects from the same hierarchy, like a list of different shapes?
Ada's got a neat way to do that. The guide talks about using a general access type to the corresponding class-wide type. Sounds a bit formal, but think of type reference as access all object class.
Object class. What does that apostrophe class mean exactly?
Think of object class as meaning the class of types rooted at object. It includes object itself and any type derived from it, like circle, point, whatever. It's like a wild card for the whole family.
Ah, okay. So that reference type can point to any kind of object in that hierarchy.
Exactly. So you can build, say, an array or list of reference and store pointers to circle objects, point objects, all mixed together. You get a heterogeneous collection, but you access them all through that single homogeneous reference type interface. It's very powerful.
Very cool. But for that to work reliably, the behavior of operations on these different types needs to be consistent, right? You need to be able to swap them out.
Absolutely. And that leads directly to the substitutability principle, especially for what Ada calls dispatching operations, the ones that can be overridden. The guideline is pretty clear here.
Let me guess. It's about conforming to expectations.
You got it. The implementation of the dispatching operations of each type should conform to the expected semantics of the corresponding dispatching operations of the class-wide type T class.
Meaning?
Meaning, if you have an operation execute on transaction class, then any specific execute implementation, say for pay transaction, has to behave like a transaction's execute is expected to behave. You shouldn't need to know the gritty details of every single derived type just to use the base class interface reliably.
So if the rule for transaction is, if isValid is true, then execute must succeed and set has executed to true.
Then the pay transaction execute must follow that same rule. It can do different things internally, but the overall contract, the semantics, must hold.
What about errors? Like if isValid is false?
Good question. The guide suggests defining specific exceptions. Maybe execute is defined to raise transaction, is not valid if the transaction isn't valid. Then all implementations of execute in that hierarchy should raise that same exception in that situation. It maintains predictability for anyone using transaction class.
Predictability is key. Okay. Now, Ada often gets praised for reliability. Does it have features for managing things like memory automatically, avoiding leaks?
Oh, definitely. That brings us to controlled types. The guideline here is, consider using a controlled type whenever a type allocates resources that must be deallocated or otherwise cleaned up.
So not just memory, but maybe files, network connections, locks.
Exactly. Anything that needs explicit cleanup. It's Ada's way of automating resource management. Think of deriving your type from ada.finalization.controlled.
Like a built-in RAII, resource acquisition is initialization pattern from C++, but maybe more explicit.
Sort of, yeah. If you have, say, a linked list package, list derived from controlled, when a list object goes out of scope, its finalized procedure is automatically called.
Ah, so finalize is where you'd put the code to walk the list and free all the nodes.
Precisely. You don't need a separate destroy list call that someone might forget. It's automatic. Prevents leaks, double freeze, all those headaches.
That seems really useful. Does it handle assignment too, like copying lists?
It does. Controlled types actually have 3 automatically called operations. Initialize when an object is created, finalize when it's destroyed, and adjust, which gets called during assignments. Adjust is clever. It typically finalizes the target object first to release its old resources before copying the new value over. It handles self-assignment correctly, too.
Wow, okay. That's quite thorough. Takes a lot of burden off the programmer.
It really does. Now, the last piece of this foundation is abstract types.
Abstract types, like interfaces or pure virtual classes in other languages.
Similar concept, yeah. The guideline suggests using them in creating classification schemes or for developing different implementations of a single abstraction.
Okay, give me an example.
Think about a bank account package. You could define bank account type as an abstract tag type. That is, abstract tells Ada, nope, you can't create an object of this type directly.
It's just a template, a concept.
Exactly. Then you define abstract operations on it, also marked as abstract, like open, close, deposit, withdraw, balance. These operations might have no default implementation or just a very basic one.
So they must be implemented by concrete types.
Right. A savings account type would then extend bank account type but would not be abstract itself. Because the base is abstract, Ada forces savings account type and any other non-abstract derived type like checking account type to provide concrete implementations for all those abstract operations, open, close, etc.
I see. So it guarantees that you only ever create fully functional leaf objects. You can't have a half-baked bank account floating around.
Precisely. It enforces completeness and consistency in your hierarchy.
All right, that covers the foundations pretty well. Let's move into section 2. Operating on tagged types, getting into the semantics and syntax, the real nitty-gritty.
Okay, so we have operations on these types. We already touched on abstract operations. They have no meaningful default. They force derived types to provide an implementation.
And the alternative.
Primitive non-abstract operations. These do have a meaningful default implementation in the base type. Derived types can override them if they need specialized behavior, but they don't have to.
Makes sense. And there was that guideline about exceptions when overriding.
Yeah, super important. When overriding an operation, the overriding subprogram should not raise exceptions that are not known to the users of the overridden subprogram. It's about maintaining the contract. Don't surprise callers with unexpected errors.
Keep the behavior predictable. Now, you mentioned something subtle earlier, redispatching.
Ah, yes. Redispatching documentation. This is crucial for maintainability. If a dispatching operation, one that can be overridden, internally calls another dispatching operation on the same object.
Like Operation A calls Operation B on self.
Exactly. And especially if that internal call to Operation B is intended to potentially use an overridden version from a derived type, then that internal call, that redispatch, must be documented in the package specification.
Why document that internal detail? Seems like implementation leakage?
It's about avoiding hidden dependencies and subtle bugs. Think about the classic geometry example. Square derived from rectangle. This is usually a bad idea because their fundamental properties differ, right? A rectangle's width and height can change independently, a square's can't.
Right. Setting the width of a square should also set its height.
Exactly. So maybe a better design is square and rectangle, both derived from an abstract any rectangle. Now, suppose any rectangle has an area function defined as width height.
Okay.
Inside that area function, the calls width r and height are actually redispatching. Ada might write it explicitly like with any rectangle class r to ensure it calls the potentially overridden width for whatever specific type r happens to be at runtime.
Ah, so area relies on width and height, behaving correctly for this specific object type.
Precisely. If that internal redispatching isn't documented, someone creating a new rhombus type derived from any rectangle might override width or height in a way that breaks the implicit assumptions of the area function, leading to weird results. Documenting the redispatch makes that internal dependency explicit.
Okay, I see. Transparency avoids accidental breakage. Very Ada. Now, what about class-wide operations?
These are great for code reuse. The guideline says use them when an operation can be written, compiled, and tested without knowing all the possible descendants of a given tag type.
Meaning the operation works generically on the whole class.
Yes. And they're also good for operations that you don't intend to be inherited or overridden by derived types.
Can we use the geometry example again?
Sure. Imagine a moment function maybe calculating moment of inertia or something. If it just needs the object's position and area, you could write it to accept object class.
So it takes any object derived from object?
Right. Inside moment, when it needs the area, it calls the area function. Because the input is object class, Ada automatically dispatches to the correct area function at runtime, the one for circle or square or whatever specific type was passed in.
So you write moment once, and it works for all current and future shapes.
Exactly. No need to duplicate the moment logic for every single shape type. Huge win for extensibility.
Definitely. Okay, let's talk constructors. You mentioned Ada doesn't have a special keyword.
Correct. An Ada constructor is just an operation, typically a function, whose job is to return a properly initialized object of a certain type.
So how do you best manage constructors in an OOP hierarchy?
There are some key guidelines. First, avoid declaring a constructor as a primitive abstract operation. This usually causes more trouble than it's worth because derived types often need different parameters.
Okay, don't make them primitive abstract. What else?
Consider splitting the initialization and construction. You might have a create function that allocates or declares the object, and then it calls a separate initialize procedure to set its state.
Why split them?
Flexibility, especially in hierarchies. Also, the guide suggests, consider declaring a constructor operation in a child package.
Aha, child packages again. Like game.constructors.makePiece. Or for the split example, maybe a vehicle package with create calling initialize, and then a car package might have its own create that calls the base initialize, and then does car-specific setup.
Exactly that kind of pattern. Putting constructors in child packages or separating creation from initialization avoids inheritance problems. If a base class constructor is primitive, a derived class might inherit it, but that constructor might not know about the new fields added in the derived class, leading to incomplete initialization. Keeping them separate gives you the freedom to define the right initialization parameters at each level of the hierarchy.
That makes a lot of sense. Avoids awkward inheritance constraints. Now, equality. The operator. This can be tricky in OOP.
It really can. Ada's guideline is direct. When you redefine the operator on a tag type, make sure that it has the expected behavior in extensions and override it if necessary.
What's the specific subtlety here in Ada?
Okay, let's go back to object with x, y, and circle, adds radius. Suppose object package redefines to mean are the xy coordinates within epsilon distance.
Okay, approximate equality for position.
Now, you derive circle. If you don't override in circle package, the inherited operation does something interesting. It applies the overridden logic, proximity check, to the inherited components, sy, but it applies predefined equality, exact match, to the new component, radius.
Whoa, wait. So two circles can be considered equal if their centers are close and their radii are exactly the same?
Yes, if you just inherit the base without overriding it for circle, it's different from other inherited operations which would only apply the base logic to the base part. Inherited equality automatically covers all components, using redefined logic for the parent part and predefined logic for the extension part.
So if you wanted the radius to also use an epsilon comparison, you must override specifically in circle package to handle both parts appropriately.
Correct. You have to explicitly define the full equality semantics for the derived type if the default combination isn't what you want. It's a common gotcha.
Good to know. Okay, last point in this section. Polymorphism. We have dynamic polymorphism via class-wide types and static via generics. How do you choose?
The guideline offers good advice. Consider using class-wide programming for runtime, dynamic polymorphism when constructing larger, reusable, extensible frameworks.
So big systems where flexibility at runtime is key.
Right. But conversely, consider using generics to define a new type in terms of an existing type, either as an extension or as a container, collection, or composite data structure.
So generics are better for what kinds of situations?
Think about defining reusable containers like stacks or lists where the element type could be anything, even unrelated types. A generic package stack type element is private. It's usually better than, say, a package stack where element is a tagged null record and all stack items must inherit from it.
Why is the generic preferred there?
Generics give you static polymorphism type safety checked at compile time. They are great for smaller, self-contained, reusable algorithms or data structures. The potential downside is code bloat if you instantiate them many, many times for large systems, as each instantiation can generate new code.
Whereas class-wide programming, with its dynamic dispatch, avoids that code generation issue but has the runtime overhead of dispatching.
Exactly. Class-wide programming is often better suited for the backbone of large subsystems where you need runtime flexibility across related types within a hierarchy, and you want to avoid generating lots of specialized code instances. It's about picking the right tool for the scale and the type relationships involved.
Makes sense. Choose based on the problem's needs, static safety, and reuse for smaller units via generics. Dynamic flexibility for large frameworks via class-wide types.
That's a good way to summarize it.
All right, let's move into our final section, Section 3, Advanced Concepts. Starting with visibility, controlling who sees what is always critical.
Absolutely essential for good design, especially with inheritance. The guideline for managing visibility for derived tag types is very precise.
Let me guess. Child packages again.
You're catching on. Define a derived tag type in a child of the package that defines the base type if the implementation of the derived type requires greater visibility into the implementation of the base type than other clients require.
Okay, so if the child needs to peek under the hood of the parent more than regular users do.
Exactly. Think about a generic stack implementation. You might have generic stack defining an abstract stack type with private components like the storage array and maybe a size field.
Okay.
Then you might have a child package, generic stack, generic bounded stack, which implements the concrete stack. Its push and pop operations probably need direct access to that internal size component of the parent's abstract stack type to check for overflow underflow and update the count.
Right. They need intimate knowledge.
But you don't want every user of generic stack to see and potentially mess with size. By putting generic bounded stack in a child package, it gets the necessary visibility into its parent's private part, while other clients using the stack just see the public interface. It maintains encapsulation for the outside world while allowing necessary access for the implementer.
Clean decoupling. Nice.
Mhm.
Okay, the big one, multiple inheritance. How does Ada tackle this? I hear it doesn't have a direct inherits XY syntax.
It doesn't, not like C++ or Python might. Instead, Ada provides, as the guide calls them, building blocks, things we've already seen. Type extension, generics, but also type composition and access discriminants.
So you compose the effect rather than having one keyword.
Pretty much. The guidelines suggest different strategies. First, consider using type composition for implementation.
Inheritance.
What does that mean, implementation inheritance?
It means you want to reuse the implementation of another type, but not necessarily its interface or its is a relationship. Imagine you're building a hashed set. You want it to behave like a set, the interface, add, remove, is member. Right.
But you want to implement it using a hash table for efficiency. So your hash set record would contain a hash table object as a component. The hash set operations, add, remove, would then call the corresponding operations on the internal hash table component to do the actual work. You're composing the implementation, not inheriting it in the typical is-a sense.
Okay, using an object internally, what's the next building block?
Generics for mixins. The guideline. Consider using a generic to mix in functionality.
Mixins,
Yeah.
like adding optional features.
Exactly. Think GUIs. You might have a base window type. You could have a generic package, say label mixin, that takes any type derived from window as a parameter.
Okay.
Inside the generic, it defines a new type, maybe window with label, which extends the input window type by adding a label component and overriding the display operation to draw the label.
Ah, so you instantiate label mixin with your specific window type, and you get back a new window type that also has a label.
Precisely. And you can chain these. Instantiate label mixin with basic window to get window with label, then instantiate border mixin with window with label to get window with label and border, then menu mixin. You build up functionality layer by layer using generics. It's very flexible for combining features without complex inheritance trees.
That's a powerful pattern. Okay, what about the most complex case, the full multiple inheritance?
For that, Ada offers access discriminants. The guideline, consider using access discriminants to support full multiple inheritance. This is definitely advanced data.
What kind of situation needs this?
The classic example is something like an account, an interest-bearing checking account.
Right.
It really needs to act as both a savings account and a checking account simultaneously, sharing their core behaviors.
Not just implemented using them, but really be both.
Kind of, yeah. You might define the NO account object record to contain actual savings account.object and checking account.object components. The tricky part is making operations work correctly and managing the identity. Access discriminants allow the object to hold a reference to itself or parts of itself in a constrained way, enabling these complex relationships where an object effectively embodies multiple parent types. It allows controlled self-reference to tie the different aspects together.
Wow, okay. That sounds intricate but powerful. So Ada forces you to be explicit about how you're combining things rather than just listing parents.
Exactly. The rationale is clarity and avoiding the ambiguity and potential problems of direct multiple inheritance, especially when the parents aren't closely related or you're mixing is-in and has-a relationships. Ada gives you specific tools, composition, mix-ins, access discriminants to build the structure you actually need.
So wrapping this up, we've seen Ada's approach to OOP is quite distinct. Tag types are central, type extension defines the is relationship, child packages manage structure and visibility.
And controlled types handle resources, abstract types enforce completeness, and you have specific ways to handle constructors, equality, and even multiple inheritance effects using these building blocks.
It's definitely a language that favors explicitness and control. The syntax might look different, but it enables some really robust and maintainable designs.
Absolutely. Understanding these Ada-specific guidelines and patterns is really the key. They help you leverage the language's strengths and avoid those potential gotchas, turning them into, well, elegant solutions.
So the final thought for you, the listener. As you think about your next system, how might Ada's very nuanced take on object-oriented design, that precise control over visibility, the different ways to achieve inheritance effects using these building blocks, How might that challenge or maybe even enhance how you currently think about OOPP?
Definitely something to ponder.
It is.
Yeah.
Until next time, keep diving deep.